Welcome back to The Explainer. Today, we're unraveling the fascinating world of a specialized superalloy built for the absolute most extreme industrial environments on Earth. It's a material that engineers rely on when failure simply isn't an option. We're talking about ASTM B444. Get ready because we're going to explore how one incredible specification actually acts as a hero with two very distinct faces. Picture this. You're designing a system for a nuclear power plant, or maybe a massive petrochemical refinery that's handling sour gas. The temperatures are scorching, the pressures are immense, and the chemical environments are, frankly, incredibly aggressive. So, how do industries handle these extreme conditions without catastrophic piping failures? What material out there survives prolonged exposure to 1,000 degrees Celsius without melting, cracking, or just completely dissolving? Well, the answer lies in ASTM B444, which is also known by its Unified Numbering System designation, UNS N06625. Now, you might actually know it by its popular commercial name, Inconel 625. But specifically, ASTM B444 refers to this exact nickel, chromium, molybdenum, columbium alloy when it's formed into cold-worked, seamless pipe and tube. It is an absolute industrial powerhouse, purposefully engineered to maintain its strength and resist heavy corrosion across a shockingly wide temperature range. Okay, let's dive into this. Here is our roadmap for today. 1. The Extreme Environment Challenge. 2. Introducing ASTM B444. 3. The Grade 1 versus 2 divide. 4. Heat treatment and performance. 5. Real-world product applications. And 6. Specifying the right alloy. Section 1. The Extreme Environment Challenge. To truly appreciate this material, we first have to understand the massive problems it solves. The ongoing exploration of deeper offshore reservoirs, the processing of aggressive acids, and the operation of high-temperature chemical plants, they all demand higher-strength materials. Commodity carbon steel or even standard austenitic stainless steel simply cannot survive here. They'll pit, they'll crack, or they'll literally just dissolve. But if you look at the standard's chemical composition, it reveals a secret weapon, a minimum of 58% nickel. This massive dose of nickel, combined with high levels of chromium and molybdenum, is what provides that legendary resistance against pitting, crevice corrosion, and stress corrosion cracking. Section 2. Introducing ASTM B444. This brings us to the baseline material that engineers turn to for these exact, unforgiving scenarios. The official ASTM International designation governs seamless pipe and tube, and that word, seamless, is absolutely critical here. It means the pipe is produced from solid billets by hot extrusion or piercing, and then it's followed by rolling and sizing. Because there's no longitudinal weld seam running down the pipe, the full wall thickness carries the pressure. Plus, there's no heat-affected zone from welding that could act as a weak point or a sneaky path for corrosion. It's built from the ground up for maximum reliability. Section 3. The Grade 1 versus 2 divide. Now, here's where the story takes a really fascinating turn. ASTM B444 isn't just one static material. It has a core paradox. It features two distinct alter egos that behave very differently, based entirely on how they are treated at the mill. The standard outlines two specific grades. Grade 1, which is annealed, and Grade 2, which is solution annealed. They share the exact same chemical composition, but their mechanical properties and their ideal use cases are entirely distinct. It's also vital to note that, unless you specifically request otherwise, Grade 1 is the general default supplied by manufacturers. The dividing line between these two grades comes down to one critical temperature threshold, 1100 degrees Fahrenheit, or roughly 593 degrees Celsius. Grade 1 is designed and normally employed for service temperatures right up to 1100 degrees Fahrenheit. But the very second your operating environment crosses that line, Grade 2 is the material that takes over. Section 4. Heat treatment and performance. The stark difference in performance between these two grades is a direct result of their heat treatment. During manufacturing, Grade 1 is typically annealed at a temperature somewhere between 1600 and 1800 degrees Fahrenheit. This gives it excellent ductility and corrosion resistance. Grade 2, on the other hand, is solution annealed at a much higher temperature, specifically above 2000 degrees Fahrenheit. And pushing the heat treatment past 2000 degrees doesn't just warm it up, it fundamentally reorganizes the internal atomic and metallurgical lattice of the whole alloy. It's like rearranging a giant puzzle. Now, what's really interesting about this is that the extreme heat treatment produces a highly counterintuitive result. You'd probably assume that treating a metal at a higher temperature makes it stronger across the board, right? But if we look at the minimum yield strength, grade 1 requires 60 ksi, while grade 2, our high-temperature hero, actually drops down to 40 ksi. The mechanical properties data verifies this completely. Grade 1 boasts a minimum tensile strength of 120 ksi and a yield of 60 ksi, but drop down to grade 2 and the minimum tensile strength falls to 100 ksi, with the yield at 40 ksi. Both of them maintain a 30% minimum elongation, but grade 2 is undeniably softer right out of the mill. And this brilliantly illustrates the deliberate engineering trade-off at play here. Grade 2 sacrifices that initial tensile and yield strength to gain something much more important for its specific environment: superior long-term creep and stress rupture resistance. You see, when a pipe is operating at 1500 or 1800 degrees Fahrenheit under immense pressure, the primary failure mode isn't just bursting instantly, it's creeping. It's slowly deforming over time and eventually rupturing. The higher temperature solution anneal of grade 2 gives it the absolute perfect metallurgical structure to resist that high temperature creeping. Section 5, Real-World Product Applications. Let's connect these metallurgical facts to reality. Where are these specific pipes actually getting installed? Well, because grade 1 retains excellent overall strength and flexibility right alongside its incredible corrosion resistance, it absolutely dominates environments operating below 1100 degrees Fahrenheit. You're going to find grade 1 seamless pipes deep underwater in marine applications, carrying highly corrosive fluids in oil and gas production, acting as aerospace ducting, and transporting extremely aggressive acids in chemical processing plants. But grade 2? That thrives where things get truly extreme. It's heavily preferred in hydrogen production, specifically in catalyst tubes for hydrogen dissociators operating anywhere from 700 to 1000 degrees Celsius. It is also found right in the heart of nuclear power steam generators, where it faces both immense heat and the unique complex challenge of radiation-induced embrittlement. You'll even find it in the exhaust systems of high-performance gas turbine engines. Section 6, Specifying the right alloy. Understanding all of this is absolutely crucial because project planners and engineers must choose the exact right grade to ensure the safety and longevity of their systems. Let's look at one final, highly specific use case where getting this right is basically irreplaceable. In processes like methane reforming or ammonia dissociation, you have a very hydrogen-rich environment. Ordinary metals absorb this hydrogen, they become brittle, and they shatter under pressure. It's a nightmare. But the extremely high nickel content of ASTM B444, especially when it's processed as grade 2 for the high heat of a dissociator, makes it highly resistant to hydrogen embrittlement. It just continues to perform safely where other metals would literally turn to glass. So the crucial point is that making the right metallurgical choice is about massive economic and safety value. Seamless nickel alloy pipes are not cheap. They command a real premium, and the lead times can be pretty long. But because they're designed for extreme longevity, they drastically reduce facility downtime and future replacement costs. You know, the most common and potentially disastrous mistake in the industry is ordering by trade name alone. Simply asking a supplier for Inconel 625 pipe is incredibly dangerous. You have to clearly define your operating medium and your operating temperature, and then explicitly specify ASTM B444 and exactly whether you require grade 1 or grade 2. That single piece of documentation is the entire difference between a safe, traceable pipeline and a catastrophic multi-million-dollar failure. And that brings us to the end of our deep dive into ASTM B444. As you review your next major engineering challenge, or even just think about the systems powering your local infrastructure, ask yourself, what is the operating temperature? Will your piping cross that 1100 degree Fahrenheit threshold? Knowing the answer to that could be the difference between a system lasting a century or failing in a week. Keep learning, keep building safely, and we will see you on the next explainer.